Hello everyone, in this theory C-car tutorial number 47 we will explain the minority carrier diffusion starting with a basic semiconductor experiment and followed by a liquid analogy to explain the diffusion current and electrons-holes recombination. We will finish by an animation to follow and be focused only on electrons crossing a p-n junction where holes are just considered as available low energy position and not really as a positive moving charges. Before to go further, it is interesting to review the basic semiconductor experiment. The first experiment is the minority carrier concentration versus time. We take a semiconductor n-doped, so majority carriers are the electron in the conduction band, and we will plot the minority carrier density versus time. At the thermal equilibrium, the minority carrier density is noted Pn0 if n is doped with nd atoms by centimeter cube. The Pn0 equal ni squared divided by nd. If the semiconductor receives photon energy higher than the band gap energy of 1.2 electron volt for the silicon, electrons get energy to jump in the conduction band, creating holes in the valence band. So, holes minority carrier increases from Pn0 to Pn. During the continuous light, the J generation is constant and the hole concentration versus time dPn over dt is constant too. From this equation, we get that GTP equal Pn minus Pn0. At t equals 0, the light is stopped, so generation G equals 0, and the hole concentration Pn decreases exponentially to the Pn0 minority carrier density at the thermal equilibrium with the lifetime tau p. This means that all the electrons in the conduction band go back in the valence band to be recombined with holes, so hole concentration decreases versus time. The second experiment is the minority concentration versus distance. We take the same semiconductor n-doped material, so majority carriers are the electron in the conduction band, and minority carrier equal Pn0 equal ni squared over nd at the equilibrium if no light. The semiconductor received photon energy higher than 1.2 electron volt on the left side. We will plot the minority carrier density versus the distance x from 0 on the left side to the right side x. With a continuous light at x equals 0 means left side where the light is touching the semiconductor, the Pn at 0 is constant. Thus holes minority carrier continuously created by the light diffuse in the silicon to the right with a diffusion coefficient capital D, but decreasing exponentially to come back at the minority hole concentration Pn0. The Lp is a length hole diffusion which is in the order of 1 cm for silicon and germanium, but 0.01 cm for ASGA. The formula changes if the semiconductor length is lower than the diffusion length. In the theory C-car tutorial number 43 and 44, we said that the free electron in a crystal could be compared with a molecule in a gas following the same perfect gas law. So we could speak of electron pressure. To explain the electron diffusion, this analogy makes sense again. On the left, I show a high and low pressure gas in two separated volumes. Of course, if we connect both volumes, the high pressure molecules will move to the low pressure area as shown in the animation. Now we use a p-doped silicon bar with the electron minority carrier with a concentration by centimeter cube of n0 at the thermal equilibrium, represented by the dot in the p-doped silicon. If the silicon bar received photon energy higher than 1.2 electron volt on the left side, the electron will increase their energy to go in the valence band, so the free electron density will increase at x equals 0 to n at 0. As for the gas analogy, those electrons will diffuse to the right direction in the silicon bar. For those electrons, diffuse means move, and moving electrons means current. This current is called a diffusion current. For a long time, it was pretty hard for me to realize what was this diffusion current until somebody gave me an analogy with liquid to really understand the current diffusion. Today, I would like to share this analogy with you, hoping that this analogy explanation will help somebody else. You need to imagine a constant current water in a channel, which means with constant water height. Then at x equals 0, the bottom of the channel soil becomes permeable, so the water infiltrates into the soil. As a result, the height of the water in the channel will decrease as water flows over the permeable soil. Because of the water pressure due to the height, of course, the height of the water channel decreases faster at x equals 0 and goes slower as we advance on the right side to get a 0 height at the end. It is intuitive that the height liquid variation, the slope S0, is proportional to the diffusion current IDiff0 going through the channel section at x equals 0, and IDiff1 crossing the section at x equals 1 is proportional to the slope S1. Of course, when x increases, the slope equals 0, which means that water current does not diffuse anymore. The water height in the channel represents the minority carrier density in the silicon. Now, if we are looking at the water infiltrated in the soil versus x, represented by arrows directed to the bottom, we will see that arrows are stronger at x equals 0 and 0 when x is high. This water infiltration in the soil is the analogy with the recombination current. The diffusion current IDiff equals 0 is equal to the recombination current, or infiltrated water from x equals 0 to x equals 1, plus the remaining diffusion current at x equals 1 equal to IDiff1. At x equals 2, the remaining diffusion current equal IDiff2 equals 0, so the current IDiff equals 0 is equal to the total of the recombination current represented by the water infiltration, see all arrows. In this slide, we can see the water analogy for the diffusion current in the upper channel represented the conduction band with higher energy, and the water infiltration analogy for the recombination current, see blue arrows, and collected in the lower channel representing the valence band with lower energy. At x equals x1, the diffusion current is maximum. At x equals x2, the diffusion current becomes 0, but all the infiltrated water representing the recombination current is collected in the lower water channel, and at x equals x2, the totality of the upper channel means the maximum diffusion current is replaced by the maximum conduction current. Between 0 and x1, the upper channel water represents the maximum current in the conduction band, and the lower channel with 0 water represents the 0 current in the valence band. The diffusion current goes down with an exponential shape. The diffusion current is a current crossing the section at different value of x, from the maximum current at x equals x1 to almost 0 current at x equals x2. The infiltrated water or recombination current is collected in the valence band, so the conduction current increases exponentially from 0 at x equals x1 to I max at x equals x2. The upper water channel represents the electrical flow of free electrons in the conduction band in the n-doped material with high energy electron. The lower channel represents the electrical flow of electrons in the valence band in a p-doped material with low energy electrons. Electrons use the lack of electron or hole to move in the p-doped material. The left picture shows the conduction and valence band in the p-doped side material. The blue curve represents the density of the electron minority carrier diffusion in the p side. The density is equivalent to the height of the water in the water analogy in the upper water channel. The red curve represents the electron density in the valence band. The electron density is equivalent to the height of the water in the water analogy in the lower water channel. The notion of holes as a positive charge is very practical to explain the p-doped material and the p-n junction. But at the same time, we know that the current is only due to moving electrons. So, in this animation, I decided to follow and be focused only on electrons crossing a p-n junction. The p-n junction has the same concentration doping, Nd and Na, for N and P with 10 to the power of 16. The black dot represents electron. The white circle represents the lack of electron used for the atom valence link in the valence band. If we decide arbitrarily that 203 electrons in blue arrive on the N side in the conduction band, after crossing the p-n junction, we should find the same 200 electrons in red getting out on the p side in the valence band. As to simplify this presentation, the N and P doping are equal, so we can assume that on the 200 electrons, half of them, see the 100 electron in blue, will cross the space charge area with high energy, which means in the conduction band, and the other half electron, see the 100 electron in red, will cross the space charge area with a low energy, which means in the valence band. Let us now follow the 100 electron crossing the space charge in the conduction band. When the 100 electrons arrive in the p side, they became a minority electron carrier with high energy, but in the area where a lot of low energy positions are available in the valence band. On the 100 electrons, we can assume that half, which means 50 electrons, will use the low energy position available in the valence band. This is called recombination, and the other half electron will stay as minority carrier for a while in the conduction band. The 50 electrons coming from the conduction band will be added with the 100 electrons crossing the space charge in the valence band to get 150 electrons moving in the available low energy position in the valence band and called holes. Following the minority carrier diffusion on the 50 electron, 25 will continue to diffuse in the p area, but 25 others will use the low energy position to increase the moving electron in the valence band to 175. Then, same thing, half of the 25 will stay in the conduction band and the other half will increase the number of electrons moving in the valence band to 187. The electron going to the low energy position will continue to decrease as we advance in the p side as 6, then 3 down to 0 after 4 or 5 times the diffusion length Ln. At the same time, the conduction current due to the electron moving in the available low energy position in the valence band will continue to increase at 193, then 196 to reach finally the 200 electron with lower energy getting out on the p side. The electrons in the red circle represent the accumulated electron charge in the p side. The exponential blue curve is the minority carrier electron concentration in the p side, which decreases to the minority carrier density at the thermal equilibrium of Ni squared divided by Na. As the current diffusion is a derivation on the minority carrier density, From the concentration curve, we can plot the electron diffusion current in the p side. The conduction current in the p side is proportional to the electron's concentration, so from the electron density we can get the conduction current. Now, if we are looking on the n side, the 100 electrons noted in red crossing the space charge area in the valence band, they are formed by 50 electrons coming from the high energy electron in the conduction band, which we choose the low energy position in the valence band, plus 50 electrons taken in the valence band and leaving 50 lack of electrons or holes. All the electrons taken in the n-side valence band create an accumulation of positive charges. We do the same to get conduction and diffusion current based on carrier concentration. Of course, the total current is a sum of conduction and diffusion currents. But in summary, we started with a flow of x electrons by second in the conduction band and 0 electrons in the valence band in the n-side to get a flow of x electrons by second in the valence band using the available room due to the lack of electrons at low energy position and 0 electrons in the conduction band. Current in n-side is 3 electrons moving in a crystal with higher energy than the valence band. Current in p-side is electrons moving in the available lower energy position called holes, provided by the Na concentration of acceptor doping atom. I want to thank you for your attention. On my next series tutorial number 48, we will talk about the bipolar junction transistor invention. So, see you soon and stay tuned.